Hello. In this final unit of study, we begin what is probably my favorite part of statistics, the branch of statistics that is known as inferential statistics, when we infer conclusions based on data that we accumulated. The first branch that we studied in the first portion of the class was descriptive statistics. Once we get statistics, how do we describe it? What patterns do we see? Things like that. But now we're going to start to draw inferences or conclusions. We can test claims made by companies or by people or politicians or a variety of things to determine whether a claim is valid or appears to be invalid, not supported by the results. So here's an example for the main idea for today and kind of the type of things that we'll be considering going forward. For example, a cancer research center would be very interested in accurately identifying the average white blood cell count for a person. And that varies. Everybody might have a different count, so they want to get an idea of what's an average amount. So they're going to sample. If they do sample 100 people and find an average value, how sure, in statistics we would use the word confident, that's going to be a big word going forward, how confident are they that the actual average value that they obtained is reasonably close to the true average value of the population? How do we measure this? So there are two ways that we can estimate the population parameter, that holy grail value that we want to know, that we're going to estimate by conducting a sample. The very first thing we can do is do what's called a point estimate. As you can guess, this is a single point that we're using to estimate the true value of the population parameter. So a point estimate is a single value estimate for a population parameter. Uh, the most unbiased point estimate of the population mean that we want to know is going to be our sample mean. So the population mean, we use the Greek letter mu. We're estimating it with an x, and we put a bar over the top to denote average. Anytime you see a bar over the top in statistics, that's indicating an average. So for example, for the white blood cell count, let's say the sample of 100 people had an average of 7,000 white blood cells per milliliter. Therefore, 7,000 would be our point estimate of the population parameter. We don't know what the population parameter is. Maybe it is 7,000. Maybe it's 7,500. Maybe it's 12,000. We don't know because we can't sample everybody. So we conduct 100 people, and we're going to use that point estimate as our best guess for the true population parameter. So that's one way that we can estimate the population parameter. The second way, and is really the way that we're going to investigate in this section, because the first one's pretty straightforward. We did that in the past. You get a sample, you calculate the average. But we could also do it with an interval, give a range of values that we're using to estimate the population parameter. So an interval estimate is an interval or range of values that we use to estimate that population parameter. So although you can assume the point estimate is rarely equal to the population parameter, it is probably pretty close. You can then form an interval estimate by using the point estimate as our center and then adding or subtracting what we call a margin of error. We find that by combining the standard deviation of the population, if we know it, and how confident we would like to be. This confident is going to be related to z-scores and the normal curve that we used before. So for example, let's say in the white blood cell count, we have a margin of error of 450. That means we want to be able to go 450 above and 450 below. Then our interval estimate would be 7,000, give or take 450. So we would estimate that the population parameter is somewhere in between. If I add 450, it'd be the highest is 7,450. If I subtract 450, it'd be 6,550. So our interval estimate would be shown here in red, and our point estimate is the center. So when you use an interval estimate, you're kind of giving yourself some leeway. That's the idea. We're fairly certain, we're going to be using the word confident going forward, that the true population is somewhere in here. You know, it might be right here. It might be actually 7,250. It might be here. It might be 6,780 or something like that. But we're giving ourselves a little bit more leeway by conducting an interval. You know, the true population, it might be out here at 8,000. There are some times that, you know, our sample isn't that great, and it might have been biased. We don't know why, but it may have. And so our interval, though, is our best shot when we give ourselves a little bit of some leeway. On the prior page, it was mentioned that the margin of error is made up of two things. It's a combination of the standard deviation of the population, how variable the population are naturally, and how confident we would like to be that the interval estimate contains the population mean. The level of confidence, we denote it with the letter C, is the probability that the interval contains the population parameter, and this is important, assuming the estimation process is repeated a large number of times. Any interval that we form is either going to have the actual value or it will not. But if we conduct that interval, 100 or 1,000 times over, it will form different intervals, and our level of confidence is the probability that all of those is going to actually have the true population parameter. If the level of confidence is 90%, that means we'd be 90% confident that the interval actually contains the population parameter mean that we are after, assuming this process is repeated over and over and over again. The critical values that we use to form these confidence intervals are from our z-scores from before. So critical values are the values that separate sample statistics that are probable from those that are improbable, what we don't think would actually contain the actual population mean. For a 90% confidence interval, that would correspond to a z-score of 1.645. Why does it do that? Well, because if you have a z-score of 1.645, we tend to know that by the bell curve, that's going to capture the middle 90%. And so that's what we call a 90% confidence. If we go out to a z-score of 1.96, we know that from the bell curve that's a 95%. It gets the middle 95% of the data, so we'd say we are 95% confident. If we go out to a z-score of 2.575, we've captured 99% of the data centered on the sample mean. And so we'd say we're 99% confident. So you need to record these. These are used over and over and over again. You'll probably have them memorized soon enough, but you need to record those in your notes. One other thing I want you to notice is as your level of confidence increases, note that the z-score has to also increase, and that will increase your interval. If you want to be more confident that you're actually capturing the true population parameter, you have to make your margin of error, your interval, wider. I'm going to use a analogy of fishing. If I want to be more confident of catching fish, I need to cast a wider net, and that's exactly what we're doing. If we want to be more confident, we have to have a wider interval. The formula for the margin of error, well, we said it was a combination of the z-score, our confidence interval, and our standard deviation, is actually just the multiplication of those two. So the margin of error is the greatest possible distance that we're going to allow our interval to be different from the sample mean that we found from before. So it's the greatest possible distance between our point estimate, which was our sample mean, and the value of the parameter it is estimating for a given level of confidence. The equation is simply our critical z-score times the standard deviation of the population. And we find that by just taking the standard deviation and dividing it by the square root of n. So this is the standard deviation, that's the margin of error. Couple notes, the sample is expected to be random, and our population needs to be normally distributed, or we need to have a large enough sample. We need to have at least a sample of greater than or equal to 30. That's from our central limit theorem from before. Sometimes called the maximum error of estimate or the error of tolerance. So our margin of error is found using the following formula. It's going to be how wide our interval is. So if this is our point estimate, then how far we go out to the right and how far we go out to the left, each of those is called a margin of error. So example, let's say a survey of a random sample of 1,000 smartphone owners found the average daily time spent on the phone was 131.4 minutes with a standard deviation of 21.2 minutes, known from previous studies. State the margin of error for the following confidence intervals. Some smartphones actually tell you now, like each week, how much time you're spending on your phone, and so they're concerned with this because they're concerned with how that kind of affects daily life. So this might be an important study. If I want to find a margin of error for 90% confidence interval, well, I need to find my z-critical score. If it's 90% confident, that's a z-score of 1.645. The population's standard deviation was 21.2 minutes. I need to divide it by the square root of my sample size, which would be the square root of 1,000, and then I just type that into a calculator. And when I run it, I'm going to get a margin of error of 1.103. My units are minutes, about 1.1 minutes. If I want a 95% confidence interval, we should expect this number should get bigger. If I want to be more confident, my net needs to be a little bit wider, my interval needs to be a little bit wider. Run the exact same calculation. The only thing that's going to change is the z-critical score. The population standard deviation doesn't alter, and my sample size hasn't changed. When I run it now, I get a margin of error of 1.314 minutes. It needs to be wider, which is what we've seen. Last one, if I want to do a 99% confidence interval, then my z-critical score needs to be 2.575. I run it, and I get 1.726 minutes. You should notice what happens to the margin of error as we increase our confidence interval, our confidence level. The margin of error increases. We want to be more confident. We need to cast a wider net. Our interval needs to be wider. Hopefully that should make sense to you. I'm going to give you a chance to try. From a random sample of 48 days in a recent year, U.S. gas prices had an average value of $3.63. Assume population standard deviation is 21 cents. Find the margin of error for a 95% confidence interval. If you'd like to try it for yourself to make sure that you're picking up what we're putting down, try it now. Pause the video, come back once you've given yourself a chance to try. Okay, this is what you should have found. You should have found when you run it, your z-critical score is 1.96 because we got a 95% confidence interval. 0.21, 21 cents is our population standard deviation divided by our square root of our sample size. We get about 6 cents is going to be our margin of error. It's how much we will allow our interval to be above or below our point estimate of 3.63. Now that we know how to construct the margin of error, we can actually begin constructing our intervals. And we call these confidence intervals because they are intervals and they change based on our confidence. So a C confidence interval, it could be a 90% or a 95 or a 99 are the typical ones. Percent confidence interval for the population mean is found by taking our sample and adding our margin of error to get the high end and subtracting it to get the low end. It is the probability that a confidence interval similar to the one constructed is going to be C, assuming that the estimation process is repeated a large number of times. Here are the following steps, and this is shared in the book. The first thing is that we need to verify that our sample standard deviation is known, our sample is random, and either our population is normally distributed or we have a large sample, a large enough being greater than or equal to 30. The first thing we need is we need that middle point, we need the sample. So we need to either calculate it or it'll be given to us. We need to find that point estimate. We need to find the corresponding critical values. We can use the common z-scores, or you can always use the inverse norm. If they gave you something besides 90, 95, or 99, they gave you like an 80% confidence interval, you'd run inverse norm with 0.8. Then you need to find the margin of error, which we've done a few times now, and then you need to add and subtract that from the point estimate, and then you'll have your interval estimate. So here's an example. Let's say a college admissions director wishes to estimate the average age of all students currently enrolled. In a random sample of 20 students, the mean age is found to be 22.9 years. From past studies, the standard deviation is known to be 1.5 years, and the population is normally distributed. That's important because we didn't have a large enough sample. We only had 20 students. We're going to construct a 90% confidence interval of the population mean age. So the first thing we need to do is verify the population is known, sample is random, and population is normally distributed because we didn't have a large enough sample. Now we can use the formula for E. We need to note that our point estimate, average age was 22.9 for our sample. For a 90% confidence interval, our critical score is 1.645. You could also use inverse norm, 0.05. Mean 0, standard deviation of 1 to get your z-score of negative 1.645. Then you know the negative and positive of each other. Now we can find our margin of error. Z-critical score is 1.645. Our population standard deviation is 1.5 years, square root of our sample of 20, and we end up getting 0.552 units or years. Now I know my margin of error. I can form my confidence interval. I can make my confidence interval by adding and subtracting 0.552. This one rounded it to 0.6. That's fine. above and below my point estimate. So my point estimate was 22.9. I add 0.6, I get 23.5. I subtract 0.6, I get 22.3. So my 90% confidence interval would be between 22.3 and 23.5. We are 90% confident that the true population average age of that college is somewhere in that range. So the interpretation, with 90% confidence, we can say that the average age of all students is somewhere between 22.3 and 23.5. That's what a 90% confidence interval for this would say. I want to point out a couple correct and incorrect interpretations of those results. So the first thing is that the population's average is a fixed number. That means it is either in the confidence interval or it is not. So back here, let's say that the true average age of students was 22.5. Then it would be in there. So it's either in there, or maybe the true population average age of all students was 24. Maybe there's a lot of non-traditional students that tend to go there. In that case, it is. So it's either is or it is not in there. It is incorrect to say that there's a 90% probability that the actual mean is in that interval. It either is or it is not. There's not a 90% probability. What it does mean, though, with the 90% is if we ran that sample procedure over and over again, if we did 100 repetitions of sampling 20 students and constructed 90% confidence intervals for all of those 20 student samples, we would find about 90 of them would have the actual population mean. So for example, this one does, because here's my mean. This first one does, the second one does, the third one doesn't. For some reason, that sample of 20 was low. The fourth one does, the fifth one does, the sixth one does, the seventh one does, the eighth one does, the ninth one does, the 10th one does. We'd see 9 out of 10 on average would actually contain the true population mean, but 1 out of 10 would not. So what we mean is when we construct it, we only ever construct one of them because it takes a lot of resources just to construct one, but it does not mean that there's a 90% probability that the true population mean is in there. It either is or it isn't. The 90% means if we ran that process over and over and over again, 90% of intervals just like the one we made would actually have it. We can also use technology to get a confidence interval as well, which shouldn't be surprising based on how the rest of the course has gone. Here's an example of using a TI calculator to do it. So the first thing you need to do is hit Stat, tab over to Test, and select Z interval. I'll walk through what it looks like, but the steps are laid out there for you. It's also on the calculator sheet. Let it load. Should mention, I guess, for input, you're going to select Stats, because you have the statistics, but I'll follow it right now. So you'd hit Stat. You tab over to Tests. We're running a test. It's an interval test. And you see that you're going to choose option 7. We're going to choose that we have the statistics. Sometimes you might want to do it for data. If you had a large data set, you're going to use a list or something, but all the ones we do, we're going to be using the statistics. And then you enter the values. Our standard deviation is 1.5. The sample that we ran had an average age of 22.9. How large was our sample? It was smaller, but luckily it was normally distributed. Our confidence level is going to be 0.9. And then we asked it to construct that 90% confidence interval, and voila, there it is, 22.3 to 23.45. So it did exactly what we had. I will note, if you use the calculator on your homework, you need to, 1, justify why you can use the margin of error. You need to say the standard deviation is known. We have a random sample, and either the distribution is normal or we have a large enough sample, and then you need to write down what you typed in. So you need to write down this stuff right here. Last thing we're going to do is kind of work a situation backwards. So recall our margin of error calculation is found by taking our critical score and multiplying by the population standard deviation divided by the square root of n. However, sometimes we need to know how many people we need to sample in order to get some given margin of error. So let's say I want to be within a certain amount above or below. So I'm defining how wide my interval needs to be. I want to know how many people, how many items should be in my sample. So what we're going to need to do is solve for n in this equation. So I rewrite my equation. This will be some good algebra review. I'm solving for n. So the first thing I need to do is undo multiplying by the z critical. So divide both sides by zc. I will then have e over ZC is going to equal my population standard deviation divided by the square root of n. And here, what you can do, you can either use the cross product property, which is kind of funny because we just saw, undid by dividing by both sides by ZC, that'd be fine. Or I'm going to need to multiply the n up and then solve for it. I might use the cross product property because I think a lot of people are familiar with that from before. Kind of undoes the proportion we have going on. So I end up with E times the square root of n is equal to standard deviation times that Z critical score. Now I need to solve for n, so I'm going to divide both sides by E. And then the last thing I need to do is undo the square root. How do you undo a square root? You square both sides. So the formula is this guy, n is equal to the population standard deviation times the critical score divided by the margin of error. Once I find all of that, I square it. And that tells us how large a sample we need in order to obtain a given margin of error. This is in your book. You might want to write it down, maybe write it at the top of your homework as well. So given a confidence level and a margin of error, the minimum sample size we need is given by the following formula. If the standard deviation is unknown, you can estimate it using our sample standard deviation. We'll look at that more tomorrow. Provided you have a preliminary sample with at least 30 members. So example, let's say a cancer research center wants to estimate the mean white blood cell count, like we were talking about before. They want to be 95% confident that the sample mean is within 200 milliliters of the population mean. They might say like within 200 milliliters, we think there are 200 white blood cells per milliliter. We feel good. We don't want to be any wider than that. How many people need to be in their sample? We're going to assume the sample standard deviation is about 1,100 white blood cells per milliliter. So we use the formula. The critical score, if we're going to be 95% confident, is 1.96 times the standard deviation for ours was it say 1,100? Is that right? Okay, so 1,100 divided by margin of error is going to be 200. It says the sample mean is within 200 milliliters, so within 200. And then I square it. And I just type that in my calculator. So grab a calculator, 1.96 times 1,100 divided by 200, and then square it. We need 116.2. We've got to round that up because 116 would be too little. We need 117 people to be involved in our sample in order to get those results that we're looking for. 95% confidence interval and a margin of error of 200 white blood cells per milliliter. And that is it. Thank you very much. Have a good day.